Have you ever wondered if humans could live on the moon or Mars? What roles will they play in the future of our civilization? And which one should our space programs be focusing on? You may be surprised, as I'll be addressing many common misconceptions about the subject. By the end of this video, you'll know the pros and cons of both destinations, how to deal with their unique challenges, as well as what we stand to gain for our efforts. I'm Will, and this is Mars Matters.
Mars Matters.
Don't forget to like and subscribe. With the advent of reusable rocketry, the cost of going to space has never been lower, and it sparked a new space race around the world. NASA hopes to go back to the moon in 2025, with a permanent moon base and lunar space station to follow. If all goes well on the moon, they'll send the first humans to Mars in the 2030s. That is, if SpaceX doesn't get there first. Elon Musk's rocket company, SpaceX, is racing to launch a manned mission to Mars at the end of 2029, with the aspirational goal of a 1 million-person settlement by 2050. China and Russia have agreed to collaborate on a lunar research station, while Europe, India, and many others have plans of their own. But should the moon or Mars be the focus?
You take the blue pill, you wake up in your bed and believe whatever you want to believe. You take the red pill, and I show you how deep the rabbit hole goes.
Mars is the fourth planet from the Sun, but at its closest it's still 55 million kilometers away. The Moon, at only 400,000 kilometers away, is always at least 140 times closer. But proximity isn't everything. Mars contains all the elements that Earth does, while the Moon lacks meaningful amounts of many elements important to life and civilization. Water ice has been found on both, but there's 1 million times more on Mars, and it's accessible near the surface at all latitudes. On the Moon, it's only scarcely available in craters at the poles. Mars is also twice the diameter of the Moon, and has 4 times as much land area, equivalent to all the continents of Earth put together. And although its gravity is only 38% of Earth's, it's more than twice as strong as the Moon's. So it seems there's more to look forward to on Mars. That is, if you don't mind the distance. But which would be easier to live on? Mars has a surprisingly familiar day-night cycle, lasting 24 hours plus an additional 40 minutes, while days and nights on the Moon are 30 times longer than on Earth. Mars's atmosphere is only about 1% as dense as Earth's, but the Moon's is so thin it practically doesn't exist at all. Being further from the Sun, Mars is cold, averaging negative 63 degrees Celsius. At the equator, it can get as warm as positive 30 during the day, but with a thin atmosphere, it drops to negative 70 at night. With almost no atmosphere, though, the Moon's temperatures are even more extreme. A day at the equator is a scorching 120 degrees Celsius, and at night, negative 180. That's a temperature swing of 300 degrees. Mars may be cold by terrestrial standards, but the thin atmosphere means you'd notice the temperature less, and it would be easier to keep warm. The atmosphere protects against solar flares and micrometeoroids, so with a little insulation and some regolith on the roof, we should be able to live anywhere on the surface of Mars. On the Moon, to avoid extreme temperatures, radiation, and meteorites, almost everything would need to be underground. Now that the basics are out of the way, let's get into the good stuff. Later on in the video, we'll compare the ability for lunar and Martian settlements to produce food and energy, as well as the challenges of using local resources for manufacturing. But for now, let's take a deeper look into what it takes to get to these locations in the first place.
It's one small step for man, one giant leap for mankind.
The most common argument in favor of the Moon over Mars is its proximity to Earth. It's claimed that Mars is too hard to get to, or that we'd need to refuel on the Moon before launching to Mars. Let's discuss that. Transportation to the Moon is relatively straightforward. It only takes 3 days to get there, and we have access to it all year round. The distance to Mars fluctuates as it orbits the Sun, but the closest it gets to Earth is still 140 times further than the Moon. You can only efficiently launch to Mars every 26 months, and the journey can take more than half a year. This means that reusable rockets could make many trips to the moon and back in the same time it would take to complete one trip to Mars. But distance and travel time are only part of the story. Getting to the moon requires a total change in velocity of 15 kilometers per second. Despite being much further, the 9-month trip to Mars only requires an additional 4 kilometers per second. So, does it take more propellant to get to Mars? Well, no, actually. There are ways a spacecraft can change its velocity without the use of propellant. For example, Martian gravity can help to capture into orbit. Then friction with the atmosphere can lower the orbit and provide deceleration for landing. By using the Martian atmosphere to slow down, the change in velocity that needs to be provided by the engines is only 13 kilometers per second. Since the moon doesn't have an atmosphere to slow down against, getting there actually requires more work from your engines. This is why refueling at the moon isn't necessary for a Mars mission. So far I've assumed the Moon and Mars vehicles have equal mass, but would they? Ideally, both would be reusable, and therefore have similar design requirements, such as heat shields for returning to Earth. But what about the longer travel time to Mars? For human missions, a Mars vehicle would require more robust life support systems to mitigate the effects of space radiation and zero gravity. It may also be prudent to reduce the travel time to 6 months, which may still seem long, but we've kept people healthy on space stations for more than twice that long. A 6-month trip requires going 2.5 kilometers per second faster, but total propulsive needs would still be comparable to a moon mission. Current launch vehicles in production, such as SpaceX's Starship, should be more than capable of handling these requirements. It's important to note that even when building a base for humans, the majority of transports will be with non-human cargo. And cargo doesn't require radiation shielding, life support systems, or supplies along the way, and will be happy to take the more efficient 9-month trajectory. In summary, existing technology can send humans to Mars in 6 months relatively safely, with similar propulsive needs to a moon mission. And cargo actually requires less propulsion to get to Mars than to the moon. Okay, but shouldn't we at least practice on the moon first?
Okay, when he hits the craters and starts bouncing is when he gets his rooster tail. He makes sharp turns. Hey, that was a good stop. Those wheels just locked. Mark off. Okay.
There's this perception that since the moon's closer, it's also easier to practice on than Mars. But in a lot of ways, that's not true. The moon has less gravity and more extreme temperatures, so it could be argued that we should go to Mars first to practice for the moon. In either case, there aren't many similarities between the moon and Mars, so practicing on one doesn't necessarily mean you'll be ready for the other. Some similarities include the need to mine water ice, deal with dust, and build habitats in low-pressure environments, but we can practice the first two on Earth for a fraction of the cost. Testing habitat construction on the moon would be useful, as the short signal delay to the moon allows for the convenient control of robotics from Earth. And with the Earth only 3 days away, life support testing on the moon would be safer than on Mars, but only slightly. If your rocket explodes or habitat suddenly depressurizes, it won't make much difference whether rescue is days or months away. Regardless, a lot of what's needed for Mars couldn't be tested on the moon at all, like above-ground greenhouses, converting carbon dioxide into oxygen, or landing in the Martian atmosphere. We can only launch to Mars every 26 months, so it's likely we'll be spending a lot of time on the moon regardless. But when we can launch to Mars, we should. Current technology can finally get us there. And there's a lot about Mars that the moon simply can't replicate. The moon has a lot of its own unique advantages too, that we'll be discussing later on in the video, not the least of which is its access to an abundance of solar energy. Let's talk about that next. With no atmosphere, solar panels on the moon would receive 1.8 times more energy than on Earth, and 2.3 times more than on Mars. This advantage can be pushed even further at the poles, where the sun almost never drops below the horizon. Some solar peaks receive sunlight more than 90% of the time, so sun-tracking solar panels could be 3 times more productive than on Earth, and 4 times more than on Mars, providing near constant energy. This is crucial, since elsewhere on the moon, the 2-week period of darkness from sundown to sunrise would pose a significant energy storage problem. With the sun never high in the sky, but also rarely absent from it, the poles solve 2 of the moon's biggest problems. It provides a relatively consistent temperature and a place where water ice can be found. At the previously mentioned polar peaks, temperatures are stable around -50 degrees Celsius. Although a reasonable temperature, the few peaks that exist are very small and will likely only have solar panels on them. Polar temperatures at medium elevations range from -130 to -190, but considering other locations on the moon fluctuate 300 degrees between night and day, these cold but consistent temperatures are desirable for base building. The bottoms of some craters never receive any sunlight and can be colder than Pluto. Being shielded from the sun, they're the only place on the moon where water ice and other volatiles can be found. Overall, with ample sunlight, stable temperatures, and access to water ice, a lunar base at the poles is definitely doable. But will there be enough solar energy on Mars? Martian sunlight is 60% as strong as we're used to. But with a thin atmosphere, it stays this strong throughout the whole day. Therefore, we should be able to make good use of solar panels on Mars. Martian dust does build up on panels, reducing their efficiency, but humans could just brush it off. And although global dust storms can block sunlight for up to 8 weeks at a time, this only occurs every 6 or 7 Earth years. So solar power will be important on both the moon and Mars, but ultimately you can achieve 2 to 4 times as much energy per panel on the moon. Despite this, in the following section, I'll explain why a lunar settlement could actually have a harder time meeting its energy needs. Sunlight isn't available on the moon in a form useful for growing crops. Plants won't grow in a 30-day light-dark cycle, and without significant shielding, solar flares would kill any that tried. Greenhouses would be susceptible to micrometeorites and would create boiling temperatures inside if put anywhere but the lunar poles. The engineering requirements of growing plants in natural light on the moon are so immense that it's likely all plants will be grown in artificial light. Hydroponic systems are good at conserving water and increasing crop yields, but feeding any significant population this way will require unreasonable amounts of energy. On average, a hydroponic growing area of 1 meter squared requires 1 megawatt-hour of energy per year. If we assume that hydroponics can grow 20 times more food than traditional farming practices using the same amount of space, it would still require 20 square meters of growing space to feed one person with hydroponic crops. This amounts to 20 megawatt-hours of energy per year per person, or 20 to 35 square meters of lunar solar panels per person just to grow their food. On Mars, there's an atmosphere to protect crops from solar flares and micrometeorites, so inflatable plastic domes with only minimal UV shielding could be used to create cropland right on the surface. The carbon dioxide needed by plants could be pumped directly from the Martian atmosphere, and the greenhouse effect would provide warmth for a suitable climate inside. This, plus the 24-hour day-night cycle, makes Mars the only place in our solar system, besides Earth, where plants could grow on the surface in natural light. So although lunar solar panels can produce a significant amount of energy, you'd need a lot of them if you plan to power even a modest hydroponic farm. Whereas Martian crops can get their energy directly from the sun. If you plan to do anything in space economically, you have to live off the land. This means building solar panels, growing crops, and getting oxygen and water directly from lunar and Martian resources. The moon lacks meaningful amounts of carbon, hydrogen, and other elements important to life and civilization. Whereas Mars has every required element in abundance, all in easily accessible forms. Like Earth, the moon and Mars are primarily made up of oxygen and silicon. Silicon has many important uses, from increasing the quality of steel to making transistors and solar cells, but many of these applications require carbon, and manufacturing hyper-pure silicon for use in electronic devices requires both carbon and hydrogen. Carbon is virtually non-existent on the moon, and hydrogen only exists in very small quantities. This means lunar colonists will need to import raw materials to efficiently produce quality steel, biomass, and solar panels. On Mars, steel will be commonplace, and settlers will be able to build a self-expanding solar power network entirely from Martian materials. Another useful element is oxygen, which is needed for breathing and to make rocket propellant. Since oxygen makes up 60% of the moon by weight, it's often thought that it will be plentiful on the moon, but harvesting it isn't easy. Currently available methods include melting lunar regolith at temperatures greater than 1,600 degrees Celsius and running an electrical current through it. Maintaining such high temperatures is complex and, like growing plants in artificial light, energy intensive. Considering SpaceX's Starship uses almost 1,000 tons of liquid oxygen for a single launch, an easier way of acquiring oxygen on the moon will be needed. On Mars, oxygen can readily be acquired from the CO2 atmosphere. or from water, and there's enough of both to serve a growing settlement's needs practically indefinitely. Water ice has been discovered at the lunar poles, but only in small quantities in difficult to access locations, so using it for oxygen would be costly. On Mars, as a global average, 14% of the surface is water ice, and pure water ice glaciers can be found not too far from the equator. Millions of times more water exists on Mars than on the Moon, so relatively simple soil baking or ice melting technologies will be able to provide ample amounts of water on Mars. Although Martian settlements would initially require imports from Earth, in the long run Mars has by far the best potential for self-sufficiency. The Moon, however, would always require imports from Earth. So what do we have to gain from supplying these imports?
We invest far-off places with a certain romance. Better places will always call to us. Out there are no better places. These worlds have not been graced, as ours has, by life, so far at least. Our planet and our solar system are surrounded by a new world ocean, the depths of space. It is no more impassable than the last. Those other worlds, promising untold opportunities, beckon. Silently, they orbit the sun, waiting.
In addition to providing access to unlimited resources, human activity in space will drive innovation and invention, advance science, and produce all kinds of technologies useful to Earth. New industries will be formed, jobs created, and children inspired. Settlements on the Moon and Mars will enable us to test different kinds of political, social, and economic systems, and will provide new challenges with the potential to unite nations and humanity alike. With low gravity and no atmosphere, the Moon's an ideal location for certain kinds of specialty manufacturing. Considering it takes 22 times less energy to escape Earth's gravity from the Moon, we can construct satellites, rocket parts, or even entire spaceships there for use elsewhere in the solar system. In the future, the missing elements on the Moon could be obtained by parking an asteroid in its orbit to mine for resources. Eventually, there could be shipyards and propellant depots on the Moon, granting humanity easier access to the rest of the solar system. Space hotels could be constructed to support a lunar tourism industry that thrives on the relatively short travel time to the Moon and back. Lunar telescopes built on the Moon bigger than what can be launched from Earth will benefit from the minimal seismic activity, negligible atmosphere, and lack of radio signals. The Moon contains a pristine geologic history of the solar system, and its native supply of tritium could be mined for use in next-generation fusion reactors. And, when power beaming technologies mature, electricity from lunar solar farms could be used on Earth as well. Okay, so there is a lot to do on the Moon. Now, what does Mars have to offer? Having all the elements needed for a robust manufacturing industry, a Mars base could supply expeditions to the asteroid belt and beyond with tools and equipment too heavy to be transported from Earth. It could provide a resupply of propellant, water, and even food, being the only other location in the solar system suitable to grow crops for export. Asteroids contain trillions of dollars of valuable material, which Mars is extremely well positioned to access. 90% of so-called near-Earth asteroids actually orbit closer to Mars, and Mars itself orbits right on the edge of the main belt. Due to longer travel times to Mars, tourism is less likely than on the Moon. However, Mars is by far the better candidate for long-term or even permanent human habitation, so there will be a large demand for housing, which private and public companies can compete to supply. Mars is an ideal location to search for extraterrestrial life, as it was once a warm and wet planet and contained all the conditions needed for life as we know it to exist. In the long term, Mars can be terraformed to have liquid water oceans, a thick atmosphere, and plants growing unaided on the surface. Mars alone has what it takes to support a fully self-sufficient second branch of civilization, and humanity could help it become a new home for life to evolve on even long after we are gone. It's for these reasons that we're preparing our next great leap into space. The Moon's closer, but Mars is larger, with stronger gravity, more resources, and an atmosphere to protect from solar radiation and micrometeorites. Considering the familiar day-night cycle and reasonable temperatures, Mars has prime real estate compared to the Moon. The Moon's proximity does make it more accessible, but Mars isn't exactly inaccessible. Under the right conditions, rockets can actually send more cargo to Mars than to the Moon, and a human trip can be accomplished in 6 months with existing technology. The best it gets on the Moon is at the poles, where there's plentiful solar power, but you'd have to live underground and mine water ice from frigid craters. On Mars, you could live anywhere on the surface, with all the water and resources needed for life and civilization. There's less sunlight for solar power, but it doesn't take as much energy to grow crops and meet other basic needs. Besides, Martians will be able to manufacture solar panels and create a self-expanding power base, while lunar colonists will rely on imports to make efficient solar cells. The Moon's ideal for space-based manufacturing, astronomy, and tourism, and will help us to test our technologies and access the solar system. But its proximity to Earth means it will forever be subject to earthly politics, which makes it too close to be a true backup for humanity. Due to its hostile environment and minimal communication delay with Earth, the Moon is well suited to be developed robotically where possible, in preparation for the scientists and tourists who will want to go there. Mars, on the other hand, is a place where humans can live and multiply to large numbers, a place where an actual civilization, and not just a mining or scientific outpost, can be developed. Only Mars is a viable target for true colonization. Did I miss anything important about the Moon or Mars? And which are you most excited about? Let me know down in the comments. This is my first video, but I'm planning for uploads monthly, so be sure to subscribe and click that notification bell for more videos about humanity's journey to the stars. And, as always, stay curious about Mars Matters.